All right, have you ever stopped and wondered what everything is really made of? I mean, everything. Today, we're going to pull back the curtain on reality itself. We're going to decode the surprisingly simple, elegant rules that build our entire world, from a single blade of grass to the most distant galaxy. This is the universe's blueprint.
Okay, so let's just jump right in. It sounds like this huge cosmic idea, but honestly, it's super simple at its core. Every single thing you can see, touch, or even imagine, your own body, this screen, the air you're breathing, it's all built from the same tiny, fundamental building blocks. We call them atoms. It's pretty amazing when you think about it. It's the ultimate shared heritage of everything in the cosmos.
But right away that leads to a really interesting puzzle. Let's look at this. You've got wood from a tree and you've got polyester in a shirt. Believe it or not, they are made from the exact same ingredients, atoms of carbon, hydrogen, and oxygen. But, they couldn't be more different, right? One is natural, rigid, part of a living thing. The other is a synthetic, flexible fabric.
And that is the big question we're tackling. How can this tiny, shared toolkit of atoms produce the absolutely staggering variety of stuff we see all around us? To get the answer, we've got to go small, like impossibly, unimaginably small.
All right, first things first. We keep saying the word atom, but what even is an atom, really? It's time to peek inside the building block itself.
The funny thing is, the word atom originally meant something you couldn't cut or divide. But turns out that's not quite right. An atom is actually this tiny little system, with a dense, heavy center called the nucleus, and even smaller particles zipping around it. So let's meet the key players in this little drama.
First up, deep inside that nucleus, we have the proton. Think of the proton as the heart of the atom, its anchor. It's got some real weight to it, and crucially, it carries a positive electrical charge. And huddled right there in the nucleus with the protons are the neutrons. They're about the same size and weight as protons, but just like their name sounds, they're neutral, no charge. They just kind of hang out, adding some heft to the core without messing with the electrical balance. And then, zipping around that heavy nucleus are the electrons. These guys are the real live wires of the whole operation. They're incredibly lightweight and they're buzzing with a negative charge, the perfect opposite to the proton's positive charge.
So let's put this all together. Check out this little cheat sheet. You can see right away that almost all the mass, the actual stuff of an atom, is packed into that nucleus with the protons and neutrons. But the charge, well, that's a delicate dance. If you have the same number of positive protons as you have negative electrons, they cancel each other out, and the atom as a whole is perfectly neutral.
Okay, so we've met our three subatomic particles. But here's the thing. One of them is way more important than the others. It holds the key to an atom's entire identity.
And that, my friends, is the proton. The number of protons in an atom's nucleus is everything. We call it the atomic number, and it's like an atom's social security number or its fingerprint. It is the one thing that defines what that element is. If you change the number of protons, you literally change the element.
For example, take a look at hydrogen. If an atom has one proton, just one, it is hydrogen. End of story. It will always and forever be hydrogen. It's the simplest element there is.
Now let's jump all the way to the other end of the scale for things found in nature. Meet uranium. Every single atom of uranium in the universe has exactly 92 protons. That 92 is its permanent, non-negotiable signature. All right, this is huge. Now that we know every element has its own unique ID number, we can finally start making sense of it all. We can bring some order to the chaos and build a system. And that system, well, it's probably something you've seen before. It's one of the most elegant and powerful charts in all of science, the periodic table of elements. But don't just think of it as a boring old chart from chemistry class. It's a map. It's a treasure map to matter itself, all laid out in perfect order, starting with hydrogen at number 1 and just going up one proton at a time.
But here's where it gets really cool. The genius isn't just that it's in order from 1 to 118. The way it's laid out, the rows, the columns, that's a secret code. It's a code that tells us exactly how an atom is built on the inside.
Okay, let's crack this code. We'll use sodium as our example. Sodium is atomic number 11, so it has 11 protons, and when it's neutral, 11 electrons. Now, those electrons don't just fly around randomly. They fill up these specific energy levels, or shells. The first shell, closest to the nucleus, gets filled up with 2 electrons. The next one can hold 8. And what about that last, 11th electron? It gets a whole new third shell all to itself.
And this is the magic moment. This explains the entire layout of the table. The number of shells an atom is using tells you its row, which is called a period. Sodium uses 3 shells, so bam, it's in period 3. And the number of electrons in that outermost shell tells you its column or group. Sodium has 1 lonely electron out there, so it's in group I. Its address on this map isn't random. It's determined exactly by its internal structure. Mind blown, right?
Okay, now we have everything we need. We've gone from the big picture down to the subatomic and back out to the map. Now we can finally answer that first big question.
So, back to our wood and polyester mystery. Why are they so different if they're made of the same atoms? Well, it's not about the ingredients. It's about the recipe. It's all about how they're put together. Think of it like Legos. You can have a pile of red, blue, and yellow bricks. With those same bricks, you can build a house or you can build a car. Same parts, totally different structures. It's the exact same principle with atoms. The way carbon, hydrogen, and oxygen connect makes wood. A completely different connection pattern makes polyester.
And that is the core idea, the big takeaway here. The properties of every single thing in the universe, whether it's hard or soft, liquid or gas, alive or not, are all dictated by this simple atomic blueprint.
I mean, just stop and think about that for a second. The number of protons gives an element its name and its rules. And the way those elements combine, following those rules, gives our entire world its shape, its texture, and its color. It's all right there in the blueprint.
So far, we've mapped out 118 elements, and every single one of them follows these exact same fundamental rules. And that just makes you wonder, right? Is that it? Or are we just getting started? What other combinations are possible? And what new materials, and maybe even new worlds, are still out there waiting to be built from this incredible cosmic blueprint?